Hi, matriculants. I hope that you have prepped for your exams, and the following video that I'm about to do with you might be of good and help for the upcoming exams. Today we'll look at reaction rates and we'll focus a little bit on introduction, and then we'll continue with some exam questions that might be coming in exams, and I hope this will give you a good footing to answer some of those questions. Without further ado, let's continue. Okay, a couple of things that we need to focus on just to give you an idea of what this video presentation is all about. The first part is going to look at calculations. We're going to look at 6 factors that can influence the rate of the reaction, and we're going to look at how we can explain how those factors influence the reaction. And then the second part of the video will be measuring reaction rates. We'll look at certain questions from exam papers. We're going to answer those. We're going to interpret the data. And we're going to look at how that data is then obtained using experimental techniques. And then the last part of this particular video, we'll look at catalysts. We'll distinguish different types of energy distribution graphs. And we'll also look at how we can explain using the collision theory how a catalyst influences a chemical reaction. Okay, the first part here, let's just look at some basic stuff that will give us the footing for answering some of the factors that will influence a chemical reaction. Now, remember that in the textbook or in our notes, there are actually 5 factors. But one of the factors is added when you have a heterogeneous reaction. And that's a reaction where you have one of the reactants might be in this one phase and another reactant can be in completely different phase. So for instance, one is solid and the other one is a liquid. And then you're going to have a 6 factor. It doesn't really matter how many factors we have. Remember, the total number is 6, and we're going to look at what is the collision theory and how can we use the collision theory. Okay, now in the diagram over here, you can see that my first sketch in the diagram refers to, you can see it's orange and red. That's just to indicate that the temperature is going to influence the chemical reaction. Now remember, increase in temperature, increase in the rate. The second sketch refers to concentration. Definitely with liquids and with gases, we refer to concentration. Not so much with solids, and then with gases, we're looking at gas pressure. Now, increase in concentration of those substances will generally lead to an increase in the reaction rate. The same can be said for gases if they're under pressure. So if you increase the pressure of the gas, depending on the mole ratio and what's happening, you can have an increase in the reaction rate. Now, state of division refers to the surface area of a substance. If you have a solid piece, it will have generally a lower state of division compared to the same amount of substance, but it is in a powder form or granular form. In that case, the substance will have a larger surface area. We also refer to this as when it has a larger state of division. So increase in state of division means increase in the reaction rate or increase of the surface area from here to there means that your reaction rate will increase. Now, the second last one, which we don't have a sketch, is nature of reactants. Now, nature of reactants generally refer to the type of reactants that you have. Sometimes, if you're going to have reactions that are or molecules, your reactants are very simple, not very complex molecules, tiny molecules, short molecular structures, then it means the reaction will take place faster compared to complex molecules like large protein molecules or molecules that consist of lots and lots of atoms. In that case, if it's a larger, more complex molecule, the reaction rate will generally be slower. So another example here would be inorganic compounds will take a little bit faster to react compared to organic compounds. So remember, organic compounds generally consist of large molecules, large chains, and they take a little bit longer to take place. Now, the last factor here is a catalyst. Now, unlike the other factors, if you decrease those factors or you go in opposite direction, as I explained it, then you can decrease the rate of reaction. However, a catalyst can only increase the rate of reaction. So if you add a catalyst, you always increase the rate of the reaction. Okay, now that's the 6 factors explained. The next thing that we have to remember is the requirements for a reaction to take place. Now, scientists use a model, and this model is referred to as a collision theory. And the collision theory has 2 basic postulates that it says, or conditions that must be met. Both of them must be met, and not just the one. And these conditions will tell us when a reaction will take place. Now, these 2 conditions are based on an effective collision. Effective collisions are those collisions that will result in a chemical reaction taking place and products will be formed. Now remember, there are lots and lots of collisions, and molecules, reactants are always colliding, but not every collision will result in a reaction and will form products. So the first condition or requirement, the molecules must have enough energy, or you can use the word sufficient energy. Don't use it must have high energy, because some reactions do take place at very high temperatures. So use the phrase high energy, enough energy, sorry, not high energy, enough energy or sufficient energy. Okay, that's the first requirement. And then the second requirement, molecules must react and collide with each other with the correct orientation. Now, we've done in grade 11 the shapes of molecules, and we know that because of these shapes, that when molecules collide, not every collision will give us a reaction. Sometimes they will approach each other, they will collide, but the orientation will not be conducive for the reaction to take place. So remember those 2 conditions. Those conditions or requirements are essential for effective collision that will bring us products. Okay, now let's look at the next part, and we're going to look at an investigation. And here an experiment is taking place. Now, before we go into the experiment, here's a graph. Remember those factors that I've mentioned, and over here you can see them. They will generally appear on the independent axis, which is the x-axis, and they are generally the independent variables, because those are the variables you are going to manipulate. In the case of the rate of reactions, these rates of the reactions, you're going to measure, you're going to measure the time, and the shorter the time period in which the reaction takes place, the faster the reaction rate. And that is always going to be plotted on the y-axis. Now remember, there have been questions where they say rate of reactions, and in some cases, instead of rate, they say 1 divided by t, and that indicates per time unit. Be careful for that one. Okay, let's look at what the table says. Here I have a table of 3 experiments that we've conducted, and the values for temperature, concentration of sodium thiosulfate, concentration of sulfuric acid, and then the time for those experiments have been plotted in this particular table. Now, if you're looking at the first column, you can see that the temperature remains constant. It didn't increase or decrease. So we'll read the table from the top to the bottom, and we can see that the values remain the same. If we're looking at the concentration of the HCl, we can see that the values here also remain the same, so nothing different. However, if I look at the concentration of the sodium thiosulfate, I can see that that has increased from the top to the bottom of the table. And then at the same time, I can see that the time for this reaction has decreased as I go down the table. Now that's important to take note, because I can see that the reaction has occurred faster as I go from the top to the bottom, because it takes less time. Okay, For the investigation, A, name the dependent variable, and B, the independent variable for this reaction. And for A, it is the reaction rate, or you can just say it's the time that the reaction took place in. The independent variable is the concentration of sodium thiosulfate. Now, remember, don't just say concentration because we have two substances here, two reactants. If you're going to say concentration, the examiner is not going to know which substance you refer to. So be specific by saying concentration of sodium thiosulfate. And then what is the scientific conclusion? Here you're going to give me the relationship between these two columns because they are the only two columns that have changed. So the reaction rate increases with an increase in the concentration of sodium thiosulfate. Okay, you can also say that the reaction time has decreased with an increase in the concentration of sodium thiosulfate. You can't see the sodium thiosulfate here, but it is there. Okay, let's look at another experiment, and this is investigation B. And here we're going to see another table. Once again, we're going to read the table from the top to the bottom and make sure that you take note what happens. Here I can see that the values for temperature has increased, and then the concentration of sodium thiosulfate remains the same, and the concentration of the HL remains the same, but the time here has decreased, which means the rate of the reaction has increased. Now, in the same way as we indicated in the previous table, I'm going to draw arrows that will indicate to me very quickly what has happened in that table. Now, learn how to do this. You decide to read the table from the top to the bottom, or you can read the table from the bottom to the top. But I'm going to be constant and refer to that process where I read the table only from the top to the bottom. Okay, our question in this particular investigation reads as follows. In which one of the experiments, 4 to 6, is the reaction rate the fastest, and give a reason for your answer? And in this case, we're going to see that the answer for this particular one is quite easy, and that is experiment 6. It has the highest temperature, it has fastest time, or the average kinetic energy was the highest for this particular table. I would say that if they want you to give a reason, if they say give a reason by referring to the table, then you're going to say the fastest time, experiment 6 at the fastest time. So you're going to use a value, or you're going to use what you've seen here in the table to answer your question. Now, the next question is explain your answer in terms of the collision theory. Now, when you're going to give the collision theory, remember you need to give several steps that's taking place. When your temperature is increasing, you're going to say at a higher temperature, the average kinetic energy of the particles increases. Once again, we are not able to see that part here, but take note that the average kinetic energy of the particles increases. Second point is that's going to result that more particles will have enough kinetic energy for ineffective collisions to take place. So remember to use the highlighted words. And lastly, you're going to say more effective collisions per unit time is going to occur. Take note, that's a very popular question. Make sure that you know those 3 points in preparation for your exams. Okay, question 6, we're going to look a little bit closer at catalyst. And over here, I have a reaction. And my reaction is taking place where the reactants are reacting. It is reaching the activation energy, and then it decreases. You can see this is an exothermic reaction, and I'm producing products. Okay, let's see what this particular question is about. Define the term catalyst and then name the catalyst used in the following reactions. Very nice question where rates of reactions is now mixed with organic chemistry, and we know we've done this in the beginning of the year. Okay, now be careful when you give the definition for a catalyst. It's a substance that increases the rate of a chemical reaction without itself undergoing um, a permanent change by participating in the chemical reaction. Okay. Now, in esterification, remember this one. I'm sure you can remember. It's sulfuric acid. Now, here they said give the name. So more correctly will be the name. Take note, if they ask you, give the formula, you're going to give H2SO4, but you actually going to give the name. And then for additional reaction, it is platinum. If you can't remember platinum, you can either use nickel or palladium. Do take note what the examiner wants. If they want the name, provide the name. If they give you an option, the name or the formula, then you're going to provide the formula. Okay, that will be a lot easier in that particular case. Okay, now let's take a closer look at what Maxwell and Boltzmann basically told us or tried to explain to us in terms of their distribution curve. This curve is showing us how the energies are distributed of all the molecules in a particular reacting chamber. Now, here you can see, let's look at the green graph. It indicates to us over there. If you're looking at the area under the green graph, that indicates all the molecules in that particular reacting chamber that is reacting. So that includes all the reactants. Over here, take note that the probability of the particles that will have zero kinetic energy is 0. And we know that because of Brownian motion. All particles are moving. And if it's in a solid, they're just vibrating. So they have kinetic energy. So the graph will always end up in the corner and it will be 0. The highest peak of the graph would indicate, if I go right there, that's the highest probability, and that will indicate the average kinetic energy of the particles in that sample. And this graph is a particular graph and it's linked to a particular temperature. Now, if it's a lower temperature, this peak will be more to the left side. If you have a higher temperature, the graph will shift more to the right and lower. And when that happens, you find that the area under the graph here, this part of the graph will lift slightly up. Now, in the previous green graph, which I haven't explained, the area under this graph over here, this crossed out area, that indicates the particles that have sufficient kinetic energy to overcome the activation energy barrier. So at this particular point, that's the kinetic energy that the molecules need to react in order to produce products. So this is the point of the activation energy, and the area under here will represent the part of the particles or proportion of the particles with sufficient kinetic energy. If you have a higher temperature, try to imagine that the graph is moving to the right and it's lower, and then this area lift up so that you can have a larger area under the graph, and that will indicate that more particles will have sufficient energy to react. And that's basically what Maxwell-Boltzmann's distribution curve tells us. Okay, so let's go to a few graphs and see how we can use these graphs and see what the effects of the catalyst is on each type of graph. Now, they ask us to look at the potential energy time graph, a Maxwell-Boltzmann time graph, and a reaction rate time graph. Not too difficult. We're going to go step by step through these ones. In the first graph, I can see I've got a potential energy time graph. And this is the one that you've done last year. And you can see this is where the energy of the reactants, that's my activation energy, energy of the products. And I can see this is an endothermic reaction. And the graph in red, that indicates the new activation energy when you've added a catalyst to the reaction. And that will tell me that the activation energy has decreased now. And we're going to refer to that as the catalyzed activation energy. The next graph is the Maxwell distribution graph. And here I can see that the area under the graph, that will be the number of particles with sufficient energy. And then the activation energy is indicated by the solid line. If you're going to add a catalyst, this activation energy is going to decrease. Now remember, this one still exists. This is a new activation energy, which was created by an alternative route that was followed by the reactants to form products. And as a result of that, there is now a new area under the graph, and that means more molecules. So it's the red part and this bluish part or turquoise part, so that both those parts will represent the number of molecules that will have sufficient energy to have effective collisions and then form products. And that will be the activation energy, the catalyzed activation energy. Then the last graph is the reaction rate. So this graph kind of just shifts where this first part is more bending towards the y-axis, and that will be more bulge. But remember, these two parts must be connected. It will straighten out and level with the x-axis at the same point. At the beginning part and the end part of these graphs will always be at the same points. It's only in the middle where the graph will bulge up a little bit. The same over here, the beginning part and the end parts will be the same. It's only in the middle where it drops down. So take note, this one is bulging out, and this part of the graph becomes more parallel with the y-axis, and that indicates a more faster reaction that will produce the same amount of products, but it will take less time. Okay, so let's see what the next slide brings us. Now, Maxwell distribution curve, we must interpret the graphs of distribution of molecular energies. That will be the number of particles against their kinetic energy, or we have to explain how a catalyst, temperature, and concentration will affect these Maxwell distribution graphs. Now, you must be able to draw 3 graphs of the Maxwell-Boltzmann curve, and you must be able to indicate or understand how those graphs are going to be influenced by a catalyst, temperature, or concentration. If it's a catalyst, we've seen this one, the graph basically stays the same, but the activation energy just moves towards the left, where it's a lower kinetic energy, and that area under the graph is now added to the previous area to indicate an increased number of particles with higher activation energy. The concentration graph, the entire graph still starts at 0, but the entire graph is just bigger. So you can see that the area here between the two graphs will be the extra area now, and then you'll see on the activation energy, the area on the right hand side, that will indicate an increased amount of particles with sufficient energy to start the reaction and to produce products. Now, in this graph, they use 0.5 molar. Remember, that's just another unit, but it's similar to 0.5 mole per cubic decimeter. And then the last graph, we've seen what this one looks like. This is the temperature. This is the graph. Always remember, the lower temperature will be higher and more to the left, whereas the higher temperature will be lower and more towards the right. Know the difference between these 3 graphs and know how they will be changed with each factor. Okay, question 7. Here we have hydrogen peroxide, and that is converted into water and oxygen. Now, this reaction generally takes place very slowly in a container, and you'll notice that hydrogen peroxide normally will be in brown bottles, so you won't find this hydrogen peroxide in the shops or in your pharmacy in a clear bottle, because it is affected by sunlight. However, that reaction is very slow, but in the laboratory, we can speed the reaction up by adding manganese dioxide. Now remember, this is manganese and not magnesium dioxide. Take note the N and don't make the mistake by thinking it's magnesium. Now what we've done here is we have the hydrogen peroxide, we add the catalyst, and the catalyst causes the reaction to take place a little bit faster. So we're not going to included there is not there. Normally, if it's part of the reaction, it will be on top of the arrow, or you can write it below the arrow. But it's not written on the left-hand side or on the right-hand side. It's a catalyst. And the way that we're going to perform this reaction, take note that oxygen is a gas, and the gas is collected in this gas flask, and it will pump and move up the bubbles, and it will push the water down. And this method is called by collecting a gas by the downward displacement of water. So let's read what the question is all about and then see if we can answer the questions that follow. 1 gram, please take note the amount of magnesium, sorry, there I said manganese dioxide. My apologies, manganese dioxide. So 1 gram of manganese dioxide powder was added to the hydrogen peroxide with a concentration of 2 moles per cubic decimeter at the temperature of 25 degrees Celsius, which is room temperature. And the volume of oxygen, which is collected by means of the downward displacement of water, was measured. The sketch illustrates the experiment, and the graph shows the rate at which the gas was collected in the gas cylinder. So this is a volume versus time graph. Okay, so there we can see in this reaction, if you find that the graph is starting at the top, that generally will refer to a reactant. I have one reactant, so this will be the peroxide. It's a curve, it's not a straight line graph. So take note that this will indicate the peroxide, and this is the reactant. And the graph over here that starts from 0 time, that will generally refer to the product. So this could be one of the products, either the water or the gas. In our case, we're going to measure the oxygen. So this one we will look at and assume that it is the oxygen gas that is being produced in this chemical reaction. Okay, now when you're going to have a graph, remember when you're going to try to measure something, for instance, the rate, we're going to draw a tangent to the graph, and then at that point where the tangent is connecting with a curve, we can use that tangent then to measure the change over the y over the change over the x. In this case, the y will be the change in concentration over the change in time. So we're going to look at the tangent whenever we're going to work out the rate of a reaction. Okay, the first question here is define the term reaction rate. I think that one is fairly easy, and you all should get that one correct. That is the change in concentration of reactants or products per unit time. In this definition, you must mention concentration of the reactants, and you must mention products. And don't forget per unit time. Next question, name 2 factors more than the ones that you've seen in this particular experiment, which will influence the rate of the chemical reaction. Now we've seen here that we are using a catalyst, so don't mention a catalyst. So you can mention here, I've just used symbols, so you can use pressure, not in this particular case, because pressure is only applicable to the gas, and pressure is not going to have an influence on the liquid. So we're not going to use pressure. You can use temperature, that's correct. We can use nature of the reactants. In this case, no, not for this reaction. Nature of the reactants can be used, but not for this one. If you want to use that, you have to change the catalyst, or you have to change one of the reactants. The surface area, yes, you can use that. Instead of using, they've said using a powder. Here they ask us to change the reaction. They didn't say to make the reaction faster. They just wanted us to change the reaction. So we can use surface area. Instead of powder, I can use granules, or I can use a solid, and I can use concentration. Now, concentration here will refer to the peroxide. So be specific by saying the concentration of peroxide. Now, peroxide does come in different concentrations. So here you can say use a more dilute um, um, hydrogen peroxide, or you can say use a more concentrated hydrogen peroxide. Okay, so that's the answer for this question. We'll stop here, and this is the first video, and I don't want the video to be too long, and I'll be back in the second video.